Good day, everyone. You are welcome to chemistry class. We'll be looking at a topic today that says systems of naming compounds. Systems of naming compounds. When we are talking about systems of naming compounds in chemistry, there are two major ways of naming compounds according to the topic that we want to talk about. There is something called the whole or trivial name, and there is also the IUPAC name. There's IUPAC system of naming compound, which is the current system of naming chemical compounds. IUPAC is an abbreviation for the word International Union of Pure and Applied Chemistry. It is a body of chemistry that has a headquarters in Geneva, in Switzerland. The system of naming compounds according to IUPAC system involves the oxidation number of one or more elements in a compound. That's what IUPAC system makes use of. But nevertheless, we need to let you know that when you are naming organic compounds, if the chemical compound you are naming is an organic compound, you will not need the oxidation number of any of the atoms. But if the compound is an inorganic compound, you will need the oxidation number of one or more elements in the compound for you to be able to use IUPAC system in naming such a compound. Now let's move on to what is oxidation number. Oxidation number is a negative or positive number that is assigned to an atom according to a set of rules. These rules guide in assigning oxidation number to a particular atom or group of atoms. Oxidation number can be likened to valency, but not the same thing as valency. When you were being taught valency does not have sign, whether positive or negative. But also, there's a relationship between valency and oxidation number. Valency will guide you to know the oxidation number, and it is even the valency that guided in the setting these arbitrary rules that we use to assign to each to assign oxidation number to every atom. Let's take for example group 1 element. Group 1 element has valency of 1. The oxidation number is always +1. Group 2 element has valency of 2. The oxidation number is +2. Group 3 elements have valency of 3. The oxidation number is always +3. Group 4 element has valency of 4. The oxidation number varies. We can have +4 oxidation states. We can have +2 oxidation states for group 4 elements. Group 5 element has valency of 5 and 3. The oxidation state varies from one compound to another. So when we were taught valency, we were told that valency is the combining power of an element. That is the ability of that element to combine with another element. Usually, when it is combining with hydrogen, how many hydrogen atoms will combine with that particular element? So oxidation number 2 has to do with how elements combine with another element, but it's not as fixed as valency is as fixed. Valency is always fixed. You can't change valency. Group 1 element has valency of 1. There is nothing you can do about it. Just like that, group 5 elements have valency of 5 and 3. You can't do anything about it. But the oxidation number of group 5 elements vary. You can have taking for example, nitrogen belongs to group 5. You can have nitrogen existing in various oxidation states. For example, you have nitrogen 2 oxide, you can have nitrogen 4 oxide, you can have nitrogen 1 oxide, you can have triazonitrate 5. So which means all these numbers, they are the oxidation numbers, oxidation state of nitrogen in all these compounds. So it varies. So valency and oxidation, they are not exactly the same thing, but they have some relationship with one another. Now let's look at the rules that are being used in assigning the oxidation number of an atom or group of atoms in a compound. Number one of the rule is that the oxidation number of a monoatomic ion is equal to its ionic charge. The ionic charge on a monoatomic ion is also known as the oxidation number of that particular ion. For example, as you can see here, we have bromide, we have oxide, we have nitride, we have ion 3, we have ion 2 ion, we have sodium ions. The charges on each of these are -1, -2, -3, +3, +2, and +1 respectively. So the charge is the oxidation number of a monoatomic ion. Number two, the oxidation number of hydrogen in a compound is always +1. Hydrogen is always taken to be in group 1, to be a group 1 element. So with a valency of 1, the oxidation number is always +1 wherever hydrogen exists. The exception to that is in metallic hydrides. In metallic hydrides, hydrogen gain electron, and when we were being taught electrovalent combination, we were told that when an atom gains an electron, it becomes negatively charged, and vice versa. That is, when it loses an electron, it becomes positively charged. So for hydrogen to gain an electron in order to attain a duplet structure, therefore it is going to have a charge of -1, and that is why the oxidation number of hydrogen in such compound as the metallic hydrides, where hydrogen gains an electron, the oxidation number of hydrogen in such compound is going to be -1. Moving on to number 3, the oxidation number of oxygen in a compound is always -2. Oxygen always gains 2 electrons, and as a result of that has a charge of O2-. Therefore, the oxidation number of oxygen in all compounds, in most compounds, is -2. Exception to that as well, just like in the case of hydrogen, is peroxides. For example, as you can see there, hydrogen peroxide. In the example in number 2 row, the example given there was sodium hydride. So here we have hydrogen peroxide. In peroxides, oxygen has a oxidation number of -1. Number 4, the oxidation number of a non-combined element in its free state is 0. What do we mean by element in its uncombined state or in its free state? When you have hydrogen will not exist as H alone, but will exist as hydrogen gas, which is H2. The same thing is applicable with nitrogen. Nitrogen will exist as N2, oxygen as O2, magnesium being a metal will exist as Mg, and so on like that. Any element in its free state like that, the oxidation number is equal to 0. Number 5, for every neutral compound, the sum of the oxidation numbers of its constituent atom is equal to 0. You will see we will be making use of this rule number 5 and also rule number 6 when we are calculating the oxidation number of a particular element in a compound or in an ion. We call it neutral compound according to that rule 5 because the compound is not charged. It is not an ion. So the oxidation number, the sum of the oxidation numbers of all the atoms in a particular compound is equal to 0. Number 6, for a polyatomic ion is an ion that has more than one atom in it. So the sum of all the oxidation number of the atoms that make up the ion is equal to the ionic charge, to the charge on that ion. For example, we have SO4 2-, that is tetraoxosulfate 6 ion. The sum of all the oxidation numbers of the atoms that are present there is equal to -2. We also have NH4+, that is ammonium ion. The sum of all the oxidation numbers of all the atoms that are present there is equal to +1. Moving on to number 7, the oxidation numbers of other elements apart from hydrogen and oxygen that we have mentioned earlier are their respective valencies with positive values for metals and negative values for non-metals. positive values for metal and non-metals. But there is an exception to this as well, because oxidation number can vary beyond the level of valency. As we have said earlier, oxidation number is not as fixed as valencies. Valencies are always fixed, you can't change them. But oxidation number, as you are moving from one compound to another, oxidation number of an element may change. Now let's look at an example, one or two examples, to buttress our points on oxidation number. The example here says find the oxidation number of number 1, nitrogen in HNO3 and also nitrogen in HNO2. Then in number 2, we are finding the oxidation number of sulfur in SO4 2-. Now I'm going to the solution to these questions. Number 1, using rule number 5 above, we say that the sum of all the oxidation number of all the atoms that are present in HNO3 is equal to 0, as you can see there. Therefore, hydrogen being +1, we are looking for nitrogen, and oxygen is always -2. There are 3 oxygen atoms there, so we multiply -2 by 3. We equate everything to still be equal to 0. So solving the whole thing mathematically there, we have nitrogen is equal to +5. Nitrogen will be equal to +5. So that means the oxidation number of nitrogen in this compound called HNO3 is +5, and that is why the name of the compound will be called trioxonitrate 5 acid. That 5 is the oxidation number of nitrogen there. Trioxo, 3 oxygen. That is, there are 3 oxygen in the compound. The second part of that question, finding the oxidation number of nitrogen in HNO2. We did the same thing using the same rule 5 above. We equate the sum of all the oxidation number of the atoms present in HNO2 to be equal to 0, and solving it the way we solved the first one, we have nitrogen is equal to +3, as the mathematical expression of the question has been put in the note there. So getting nitrogen to be equal to +3, the name of the compound of this particular one will be dioxonitrate 3 acid. 3 in bracket there, Roman figure 3 in bracket there, is the oxidation number of nitrogen. Dioxo means there are 2 oxygen atoms there, HNO2. Then the next question there says we should find the oxidation number of sulfur in SO4 2-. So according to rule 6, we equate the sum of all the oxidation numbers of the atoms in that ion to be equals to -2, because this is an ion. Our previous examples were compounds. HNO3 is a compound, HNO2 is a compound, SO4 2- is an ion. So equating SO4 2- to be equals to -2, according to the workings that is shown there, we can now have it that sulfur is equal to +6. So which means that the oxidation number of sulfur in SO4 2- is +6. Therefore, the name of the ion can be called tetraoxosulfate 6 ion. That 6 in Roman figure inside bracket there is the oxidation number of sulfur. Tetraoxosulfate 6 ion. Tetra means 4. That is, there are 4 oxygen. Tetraoxo. So that is that about the oxidation number. And in the system of naming inorganic compounds, there is an exercise here for the students to partake in. Give the IUPAC names of the following compounds and ions by first finding the oxidation number of the elements that was stated there before the particular compound. So you find the oxidation number of the elements in that compound first, then after that you can now name the compound. You can solve it and pass your solution on to us through text message or through that email, through that phone number there via WhatsApp. Now let's move on to another subtopic under the system of naming compounds. We call it binary compounds. Binary compounds. What are binary compounds? binary means two. It has to do with two. So these are simply compounds that has just two elements in it. They are compounds that are made up of only two elements. Their names always end with the suffix "ide." You see something like "ide." Exception to that is the case of water and ammonia. As you can see there, water is H2O. There are two elements. Water is also a binary compound having nitrogen and oxygen as the constituent element. Ammonia also is a binary compound having nitrogen and hydrogen as constituent elements. But their names do not end with "ide," with the suffix "ide." These are the exception to that, but others, their names end with the suffix "ide." Examples of binary compounds are potassium chloride. As you can see, "ide," their names end with "ide." Potassium chloride, that's KCl, and hydrogen fluoride, HF, and so on and so forth. We'll still see more examples like that. Now, when you are naming a binary compound, you first of all call the metallic or the more electropositive element. The metallic or the more electropositive element is what you first mentioned, then followed by the more electronegative element, and it is that electronegative element that we carry the suffix "ide." For elements with variable oxidation states, when you are naming a binary compound, if an element has variable oxidation states, you call the oxidation number. The oxidation number of such elements are written in Roman figure inside the brackets as a parenthesis to that particular name of that element. We see example of that here. Look at these compounds and their IUPAC name that were given there. CuCl2, that is copper 2 chloride. 2 there is the oxidation number of copper in such compound, and there is another one there, Cu2O, that is copper 1 oxide. You can see copper having different oxidation number in different compound. So to specify which particular oxidation state of copper are you referring to in that particular compound, you have to put the oxidation number of the element inside the bracket as Roman figure there. So you have copper 2 chloride as the first compound there. We can also have copper 1 chloride, but to specify whether it is copper 1 chloride or copper 2 chloride that you are talking about, that is why you have to put the oxidation number of copper there. Then you have copper 1 oxide, that's Cu2O. The another example of binary compound mentioned in that place is nitrogen 2 oxide, that's NO. Then we also have N2O, which is nitrogen 1 oxide. That is the compound called laughing gas, N2O. Then we also have NO2, that's nitrogen 4 oxide. We also have CO2, carbon 4 oxides. All these compounds, they are examples of binary compounds. There is an exercise here for the students to do. They are to name the following compounds. They are to give the names of the following compounds. So you can solve them and pass the solution across to us for checking and probably for further discussion. So our next topic that we'll be moving into is going to be separation techniques. So you can begin to read ahead of that and get yourself prepared ahead of that. Separation techniques is what we'll be moving to next. So if there's any question, you can kindly inbox us or send message to us source for response. Thank you.